Here we are. Hello, greetings and welcome, friends. Today we're starting a brand new chapter, zone if you will. We're talking today about polynomial and radical expressions. Excellent. And this is going to be a very long chapter for us, but it'll be a good one. And the section that we're starting in this chapter, which clearly we're in an orangish zone right now, is pretty good. Is called Properties of Exponents. And you've seen this stuff before, but a lot of the terminology and the application of these properties will be very important throughout the rest of this course. So I take the time to go over it, you see. Yes. So let's talk about some vocabulario here. It first of all says a monomial is a single-termed expression. I'd like to point out that mono means one, yeah, like mono and stereo sound, or I don't know what the disease mono has to do with anything, but anyways, monomial reminds me of some sort of breakfast food. Monomial. A constant, all right, is a monomial that contains no variables. All right, so monomials would be something like the following, like you could have 2x, you could have had like negative 5x squared y, something like that. But a constant is a monomial that would just be like a number, like 2 or negative 7, something to that effect. All right, a coefficient is the numerical factor of a monomial. I might even say that's the number out front. All right, so in this case here, the coefficient would be 2, and in this case, the coefficient would be negative 5. Those are the coefficients. All right. The degree of a monomial, all right, is the sum of the exponents of the variables, variables, in a monomial. So what is the exponent with this x here?
1.
1. Perfect. I love it. There's actually a little invisible 1 hiding there. Not unlike some sort of, I don't know, hobbit wearing a ring, or like Harry Potter wearing some sort of magic cloak thing. Yeah, one of those, right? It was hiding there the whole time like some creeper, and you didn't even know it. It's just like hiding there. So the degree of this monomial would be 1. How about the degree of this monomial?
3.
3, because the exponent for the y was the little invisible 1, and the sum of the exponents of the variables is 3. Technically, this negative 5 also had a 1 exponent there, but that is not a variable, is it? No, that's a coefficient, is what that is. All right, a term, this will come into play a little bit later, but a term is composed of variables, exponents, and a coefficient. So this is a single term, this is a single term. Eventually, when we move past monomials, we'll have multiple terms in an expression. But for now, just understand this could be a term, and technically this is a term, right? It's just a constant term. Let's see, a power is an expression of the form x to the n. All right, we'll talk a little bit about that. And simplifying an expression containing powers means to rewrite that expression without parentheses or negative exponents. So all sorts of facts and words coming at us. I just want to make sure you're familiar with some of those. Hopefully all of them eventually, because we'll need to understand what that means. So let's derive some new things for us. So let's consider the following. Consider the following. What if I have, all right, 2 times 2 times 2? You know another way I could write that?
8.
That is 8, I agree.
2 factorial.
2 factorial is not correct,
2 factorial.
but it is the same as 2 to the third. All right, so I can write this product, right? 2 cubed even. Yep, I like it. And the reason this is true, all right, exponentiation has to do with multiplying a number by itself multiple times. All right. So how many 2's were there being multiplied?
1.
There were 3 of them. So this 3 is completely related to this 3, which is my exponent. So just to label some stuff, the 3 is the exponent. Okay. The 2 here would be referred to as the base. Okay, yep. And the entire thing, the 2 to the third. Based on our wording here, what would we be able to call that? It would be a power. It is also a type of a term, you're right. It is also a monomial, that's true. It's actually going to also equal a constant because it's going to equal 8, as one of us said a moment ago. But the entire thing would be referred to as a power. All right. Power. So you've seen some of that before. That's basic stuff. Consider the following, though. All right. Let's see if we can discover some properties of exponents here. What if I have this? What if I've got 2 squared times 2 to the third? Now what that means is 2 squared means multiply 2 twice, right? Total of twice. And I'm multiplying that by 2 to the third, which means multiply that by itself, right? Total of 3. Total of 3 factors there being multiplied. And how many are in this first batch here? 2 of them. How many are in this second batch? 3. So that's a total of, wait a minute, I could have written that as like 2 times 2 times 2 times 2 times 2, in which there was 5 of them, right? Or 2 to the 5th is correct. Well, so is there a shortcut that you see that I could take to get from here to here that you suspect would be true anytime I'm multiplying things of the same base?
Add the exponents.
Add the exponents. And that, my friends, is called the, I'll write this in green for all of our important properties, that's the product of powers property. Product of powers. I'll even say property in here, just to try to get almost some alliteration going on there. Why not, shall we? And the product of powers property, let's see, oh, where's my pen? There we are. Is this guy right here. Product of powers property. A to the m times a to the n is equal to a to the m plus n. Right? No es más mal. No es más mal. Now, could someone put into words this property? Like, what does this mean? Like if you're using the language of bases and exponents and such. Could you describe, could we Englishify this property for people that are more verbal learners?
When you have two monomials with the same base.
Okay, so I'm multiplying. When multiplying, right, two things of the same base is the key there, right? Then we can add the exponents. I like it. I like it, definitely. So let's do an example here. Exemple. Man, I keep missing my pen button clicker here. So here's our example. Let's say I'm multiplying these two monomial expressions. I've got 2x cubed y to the 5th and 5x y to the 4th. First of all, just to practice some of our vocabulario, for this first expression, or first monomial, what is the coefficient? 2, just the 2. What is the degree? 8, right, is the sum of those exponents, correct. And how about this one? What is the coefficient? 5, and the degree?
No, it's just 4.
Where'd you get? Ooh, wait.
No, there's one in front of. There would be one in front of the x, but isn't it multiplied by y?
Well, if I was asking the degree, so I know I'm
so yeah,
mixing things up. It's just the sum of the exponents of the variables, right? So, so the degree of that term would be 5. But now, if I wanted to multiply and simplify this, I want to hopefully not have a whole bunch of redundancies here. I've got many x's going on here and whatnot. We're going to hopefully be able to use some of these properties here. So when multiplying this, we can just multiply these coefficients. 2 times 5 is 10. Sounds true to me. And then I have x cubed times x to the 1st.
And then, wait, that's how it's going to be y to the 9th.
And y to the 5th times y to the 4th. right? And remember, this is that. I'm writing down a little bit more work than we'd need to, just for the sake of our notes. So this is going to be the same as, what would I do with these exponents? These exponents, if
Add
you
them
would.
and be x to the fourth.
That'd be x to the 4th and y to the 9th, right? So I would just merely add these exponents, right? So plus them and plus them, yeah. So yeah, so that would be my simplified answer. I can't do much more than that. So that is the case. So let's do another little consider here, see if we can discover another property. Consider the following. What if I've got 2 to the 3rd all squared? What does it mean to square something? Multiply it by itself, right? So like kind of total it twice. So this would be this, right? That means just 2 cubed times 2 cubed, or 2 times 2 times 2 multiplied by 2 times 2 times 2, right? But how many 2's are there all together here? There are 6 of them, right? So this is equal to 2 to the 6th.
Okay, so when you have an exponent outside of parentheses and you're going to multiply it by the exponent inside of it.
Ooh, I like it. I like it a lot. So this 6 could have come as a result of, well, 2 to the 3rd times 2 to the 3rd by my previous property is just, right, 3 plus 3 is 6. But we just realized as a shortcut, if I have a power raised to another exponent, we can actually just multiply those, right? That's the suspicion. And it turns out it's an accurate answer. So this is going to be called the power of a power property. Power of a power. And let's see, that property is exactly as our good friend Morrow just described. Right? If I have a power raised to another exponent, all right, I can just multiply those exponents is what I would do. All right, so a to the m all to the n is equal to a to the m times n. Right? Not too shabby, friends. Not too shabby, no. So let's try a little example of doing this property real quick. Ba, 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 ba. So here we are. Whoa. Oh dear. Let's see. I'm stalling for time here. So what do you think we could do here?
We could combine the, no, you have to multiply 2 by 5, which would give you x to the 2nd times x to the 10th. And then you could combine 10 and 2, so you get x to the 12th.
So we'll leave this x squared on the outside for a minute. But using our new property, that's going to be the same as x to the 5 times 2, right? Which is x to the 10th, as he said. And like I said, I'm writing down a little more than we need to, just for while we're learning these properties. So that's x squared times x to the 10th. And now, hey, I'm multiplying two things of the same base, so I can use the product of powers.
X to the 12.
So x to the 2 plus 10 is 12. I like it. Yeah, well done. Well done. That's not too bad. Not too shabby. Right? Good stuff, good stuff. All right, let's...
So is it okay to do vertical work?
Vertical work? Yeah. Let's do another consider. See if I think I've got room on this side to discover some other fact. What if I had something like this? X to the 6th over x squared. What does x to the 6th mean?
X times itself 6 times.
Let's see, yeah, something like that, right? And x squared just means x times x. What could I do to try to simplify this a little bit?
Would you divide the...
Oh. Well, just thinking about this. Don't think about any new property. I understand you might already know the property. Yeah, this x could cancel with one of those. This x could cancel with one of those, right?
And you get 4x over. No, you get.
That'd just be plain old x to the 4, right?
Or you could have just subtracted 2 and, or 6 and 2.
Okay, or I think this is what Maura was leading into as well, but Emily sees it. She thinks that we could just take 6 minus 2 and get the 4. So this is called a quotient of powers property. Powers. I like it. I like it a lot. All right, and the quotient of powers property looks something like this. And it's actually, I like to think of the quotient of powers property as kind of being similar to the product of powers in a lot of ways. All right, because they're kind of, well, they're almost like opposites of one another, or inverses maybe is the better word. Right, the product of powers said if I multiply two things of the same base, I add the exponents. Quotient of powers says if I divide two things of the same base, I subtract the exponents. Intriguing, intriguing. So, so notice instead of multiplying, I'm dividing, and instead of adding, I'm subtracting. Right, so you can see what I'm saying. They're kind of.
Is that an equal sign?
Yeah, that's an equal sign in the middle there. Yeah. So let's try a little example of this guy. Oh, wrong color. How embarrassing. What? So let's say I've got an example of this. Let's do x to the 7th times y to the 2nd over x to the 3rd y. How about? So now this only works, by the way, when you're dividing two things of the same base. Okay? So I can't add the 7 and the 2 using a previous property because those aren't the same base. But I can deal with these guys, right?
So it's just going to be x to the 5y.
So that's going to be x to the 7 minus 3 times y to the 2 minus, oh, because there's the little invisible 1 guy there, huh? Like a hobbit wearing a ring. So this is going to be x to the 4th, y to the 1st. Or I don't even have to write that first there. Questions, comments? No? Are we good on this?
Yeah.
Okay. I didn't know if the dialogue would be worth bringing out.
Take my time.
Okay, all right. Yeah, taking your time is a good thing. All right, let's consider this. I'm throwing a bunch of these properties at you, but I know you've probably seen these before. Consider the following. What if I have x divided by x using our previous property? What would that mean I would do with those exponents? Or we could even make this x squared divided by x squared or something. I just want to have it divide the same thing by the same thing. That would be the same as x to the, what are these exponents? 1, so x to the 1 minus 1.
Negative
What's 1 minus 1? 0. Okay, so I get a 0th power. Huh. Why? How do you know that?
I just know that.
Well, what is x divided by x equal to?
1.
It's 1. Why? Because anything divided by itself is 1. Right? If you think about, right, 2 divided by 2 is 1. 7 divided by 7 is 1. Pi divided by pi is 1. 0 divided by 0 is actually undefined. That one's a little crazy. You could actually argue that equaling 0 equaling 1, but undefined is what it actually is. So, so yeah, it turns out, check this out, if this, right, divided by itself is 1 over here, and also using the previous property, I showed that that's equal to x to the 0. Therefore, by transitive property, these two guys must be equal, right? So it turns out that x to the 0 equals 1. All right, which I want you to think about that one for a little while because that one seems weird. You might be tempted to say it's 0, but it's not. It's equal to 1. So this is a 0 power property. And this property does have one stipulation. So it basically says anything to the 0th power is 1 unless that thing you started with was 0. So that's a not equal to symbol there. And yeah, it's kind of related to this similar sort of concept. Multiplying 0 by itself 0 times, or 0 to the 0th could eventually backtrack to being x to the, or 0 over 0 and still undefined. So that's the 0 power property. Okay, that one's intriguing. So let's do a nice little example of that one. What if I've got 2x to the 4th, y to the 5th, all to the 0th?
Is that a 2 or an X?
It's a 2. My z's would have a little slash through them, just so you know. Yep.
So it's going to be 2xy. 4 times 0, 0, 5 times 0, 0.
Isn't it all just 0?
Well, we could use our power of a power property and kind of actually distribute over it. It turns out that's doable. But we would get 2 to the 0, x to the 0, y to the 0. 1 times 1 times 1 is 1. Or I could have just kind of macro looked at this problem and viewed this entire thing as just being like a to the 0, right? So therefore the whole thing would have equaled 1, if you wanted to think about it that way. Yeah. Yep. So realize that even numbers or coefficients can have their own exponents, and properties of exponents do apply to those as well. Good stuff. Good stuff. Let's keep cruising. Now I just talked a little bit about a distributive property there a second ago. Actually, should I do a consider for this? I don't think I even need a consider for this, you know. I think I'm just going to give you this property. This power of a quotient. And you might realize all these words are mix and matched. The order of them are significant. So if I have like a fraction of powers all raised to another power, I just kind of view this as a little bit distributive, where you can multiply both of those by that power. So it turns out exponents, yeah, maybe I'll make an important note about this. Exponents can be distributed there we are, over multiplication and division. Never over addition or subtraction. All right, and that right there is a super common illegal mistake. So this is not true. A plus b all to the p is not equal, all right, not equal to a to the p plus b to the p. Super illegal. And that's also true if that was a minus sign on the inside there. All right, and you will be tempted, like for all of eternity, trying to do that distribution in every math class you ever take for the rest of your life. But that's not going to be true. Sorry. Bad news. Bad news, I'm sorry. Now, let's consider one more thing. One more property, and this one's a little bit weirder. Consider the following. What if I have this, x squared divided by x to the, let's just do third, keep it simple. Now, using our kind of quotient of powers property,
You want to do 2 minus 3.
right? Yeah, that'd be x to the 2 minus 3. So that's the same as x to the what?
Negative 1.
Negative 1. Huh. Huh. But if we work this way, if I worked on the left side here, x squared over x cubed is the same as x times x over x times x times x, right? And what would cancel out here?
1 of the x's. Well, 2 of the x's.
2 of the x's up top, 2 of the x's on the bottom. So I'd have, on the bottom I'd have an x. What's left up top?
Nothing. Well, 1.
A 1. So, and by the way, it turns out there's a little invisible 1 coefficient that was hiding in front of that x the whole time, like a hobbit wearing a ring, and it had a little invisible 1 exponent. Man, it's like ghosts, these 1s hiding everywhere. Crazy. Stalkers. But I want to point out this situation right here. Crazy sauce. Well, what's the exponent on this x here? 1. Could you describe what you think happened here? Or a shortcut?
Is that the x to the negative 1 would be the third one when you go over the divided by 1?
Mm-hmm.
So then you just flip it and make it positive.
Yeah, negative exponents property. All right. If I have a to the negative m, that is equal to 1 over a to the positive m. What? Craziness. Mind blown, huh? Crazy, crazy. Cray, cray, even. Also, I'd like to point out, I guess, that it works in the other way. What if I have 1 over a to the negative m? What do you think that would equal?
A to the m.
A to the m. All right. So the way I like to think about this, I think Morgan was saying it's like this was over a 1. I like to think about if it's got a negative exponent, move it downstairs and make its exponent positive. Or if it's got a negative exponent and it's downstairs, move it upstairs and make the exponent positive.
Which
Right?
is why you cannot have a negative exponent.
Yeah, which is why all the way back at the beginning when we were talking about simplifying, we said you can't leave it with a negative exponent. Exactly.
Crazy, man.
So I think that's good for now. We're going to do some more work with this later. But at least we got through all the properties today. So thanks, Internet friends. Have a great